When I look at the gigantic charging stations that Tesla has been spreading around the world, like the impressive Project Oasis, already considered the largest on the planet, it's easy to be fascinated by the cables, solar panels, and dozens of superchargers in operation. But in my view, the real impact isn't visible. It's hidden, happening behind the factory walls. What few people realize is that Elon Musk is about to take a bold step, leaving traditional lithium behind. And this isn't a simple improvement. Behind the scenes, rumors are circulating that Tesla is betting on a hybrid aluminum-lithium battery, something capable of breaking all the rules we know today in the electric vehicle sector. Interestingly, this announcement didn't come with much fanfare. During the 2025 Q2 earnings call, Musk almost casually mentioned that batteries will be everything. For those following the signals, this was no small feat. Tesla has been quietly accelerating testing of a technology that combines lightness, low cost, and performance at a level never before seen. And most excitingly, this hybrid battery is expected to power the highly anticipated Tesla Model 2, scheduled for 2026. It could very well be what finally makes electric cars truly affordable. The most intriguing thing is that this revolution isn't expected to arrive explosively, but rather discreetly, thanks to the adoption of aluminum, an abundant, cheap, and lightweight metal. This shift could solve the biggest problems of current batteries in one fell swoop. Reduced weight extends range and improves performance. Lower costs pave the way for final prices unthinkable for a Tesla until recently. And of course, safety and durability are also likely to benefit. Many people wonder, why now? The answer is simple. The market is facing a limit. Lithium is becoming increasingly scarce and expensive, in addition to relying on fragile supply chains. Worse, lithium-ion batteries have reached their physical limit, unable to evolve at the pace the industry demands. It is in this innovation vacuum that aluminum emerges as the unexpected element, ready to usher in a new generation of smarter, more efficient, and adaptable batteries. Another strategic point is scale. Aluminum is already present in virtually every industry sector, facilitating its mass adoption. And when we're talking about an entry-level car like the Model 2, this logistics makes all the difference. Elon Musk knows that the success of an affordable vehicle depends not only on the selling price, but also on the cost of production, maintenance, and supply stability. When I heard about this new hybrid battery, I immediately realized it might be the missing piece in this electric mobility puzzle. Of course, Tesla isn't the first company to explore different chemistries for power cells, but, as has become typical, the company appears to be going far beyond the obvious. The idea here isn't simply to replace lithium or reduce costs. What Tesla is proposing is something bigger, creating a new structure in which each battery element performs a strategic, coordinated, and dynamic function. It's not just about charging and discharging energy, but about optimizing this flow in real time, with maximum efficiency and thermal control. The most fascinating aspect isn't just the materials used, but how this battery behaves. Information circulating from Tesla partners and laboratories suggests that this hybrid system could deliver up to 4 times more power per kilogram than current batteries. This would mean greater range, faster acceleration, greater durability, and less wear and tear even under intense use. For the Model 2, this could be the turning point that transforms a promising car into a true sales phenomenon. If all this truly comes to fruition, Tesla won't just have overcome a technological bottleneck. It could set a new standard for the entire electric mobility sector. This revolution, as they say, won't be televised, but it's being built, cell by cell, in discreet and silent laboratories. And by all indications, the future won't just be electric. It will also be lighter, smarter, and ultimately affordable. But for all this to become possible, Tesla needed to reinvent the interaction between aluminum and lithium within the energy cell. The starting point was bold, replacing traditional copper with an ultra-thin aluminum foil, just a few micrometers thick, about 4 times thinner than a human hair. This choice is no accident. Although copper conducts slightly better, aluminum offers something crucial: lightness. And for a car that needs to be fast, efficient, and affordable, this detail makes all the difference. And it's not just a matter of swapping one metal for another. The real magic lies in the treatment and the way the aluminum is integrated into the structure. In the anode, for example, Tesla applied a microscopic layer of aluminum nanoparticles over the graphite, This layer acts as a fast lane for ions, reducing resistance, accelerating charge movement, and increasing the system's response speed. Stanford research has already shown that this type of modification can increase ion flow by up to 60%. At the cathode, the change is even more radical. Instead of using a single conductive sheet, Tesla developed a kind of sandwich, alternating layers of aluminum with highly conductive carbon paper. This arrangement creates an environment where electrons move more freely, reducing losses and increasing the battery's overall efficiency, all without adding extra weight or volume. And what about lithium in this scenario? It hasn't disappeared, but it's lost its leading role. Unlike the traditional model, lithium acts in a complementary way. Its ions, smaller and faster, are the first to spring into action during charging and discharging. They pave the way for aluminum ions, which are heavier but have a greater energy carrying capacity. It's a true choreography between two metals with different but perfectly synchronized functions. This process is called dual ion transport, and it completely changes the way energy is managed. The result? Almost immediate response when stepping on the accelerator, greater stability in continuous use, and far superior resistance to heat and mechanical stress. Another impressive detail is the gels surrounding the battery core. This soft, highly conductive material acts as an energy buffer. It regulates voltage, dissipates heat, and absorbs mechanical shocks, acting as an internal airbag. And that's not all. This gel is responsible for up to 40% of the cell's energy delivery, helping to balance the system and prevent overcharging. Unlike common insulators, it also conducts heat and electricity, making operation even more efficient. When I started analyzing the numbers for this new hybrid battery, I confess I was impressed. We're talking about something capable of achieving up to 1200 W per kilogram, a simply absurd value compared to the approximately 300 W/kg of traditional lithium-ion cells. In practical terms, this means more power with less material, as well as an energy density that guarantees greater range and much shorter recharge times. It's a level of performance that, until recently, I only saw in laboratory prototypes. Now, it's about to power an entry-level car like the Tesla Model 2. And it's no exaggeration to say that, rather than reinventing the wheel, Tesla appears to be reinventing the road. The combination of aluminum and lithium creates a kind of nervous system within the cell, in which each particle has a specific function and acts in sync with the others. The result is not just a stronger battery, but almost an electrochemical organism that thinks, reacts, and adapts in real time to the driver's demands. It is this structural intelligence that paves the way for a new generation of more responsive, safe, and future-ready vehicles. What's most impressive is how this battery behaves over time. Instead of simply aging, as conventional batteries do, the Model 2's hybrid cell is designed to act like a biological system. It senses, adapts, and even repairs itself. And that's no exaggeration. In extreme situations, such as sudden acceleration or ultra-fast charging, microcracks tend to appear in the inner layers. This is precisely where aluminum shows its strength. Suspended particles in the system automatically move to the damaged spots, filling microscopic gaps and restoring the cell's integrity. This self-healing process happens in real time, preventing small defects from becoming larger problems. Lithium also plays a crucial role. It contributes to the formation of a dynamic protective layer on the anode, called SEI, which continually regenerates to maintain stable internal chemistry. This intelligent approach extends to thermal control. Instead of relying solely on external systems, the battery itself incorporates a highly conductive gel capable of absorbing heat in situations of intense load and redistributing it evenly, as if it were a fluid circulating through a living organism. This ionized material remains active even under extreme conditions, and when a contact failure occurs, it reacts instantly to restore flow and prevent blackouts. Another innovative feature is hibernation mode. If the car is parked for long periods, whether in harsh winter weather or in fleets, the battery reduces its internal activity by up to 90%. In this kind of deep sleep, it can maintain 95% of its charge for up to 6 months. Most surprisingly, when reactivated, it resumes full operation in just 0.3 seconds, as if it had woken from a nap full of energy. This feature could redefine the use of batteries in seasonal vehicles, backup systems, and even military applications. And this almost organic behavior goes further. The battery can also react preemptively to imminent damage. When sensors detect dangerous changes in its chemistry or internal structure, it enters containment mode. In this state, it reduces activity in compromised areas and reinforces conduction in healthy regions, maintaining stable operation even in critical situations. Independent tests have shown that this hybrid cell is up to 35% more resistant to wear and tear during intense charge cycles, resulting in a significantly longer lifespan than conventional batteries, without loss of performance even after thousands of recharges. All of this completely changes the way we view an electric car battery. It's no longer just a component that stores energy and sooner or later needs replacing. It becomes an active part of the vehicle, capable of predicting failures before they occur, recovering from damage on its own, and adjusting its performance as needed. It's almost like thinking about the battery not only in terms of chemistry, but also instinct. And this analogy becomes even clearer when I consider how it responds to the environment. The battery doesn't just withstand climate changes, it changes with the climate. In extremely low temperatures, it prioritizes the use of aluminum, which is more stable and less susceptible to crystallization. In very hot regions, lithium takes center stage, ensuring more efficient cooling and smoother performance. Ultimately, what Tesla is signaling is a true paradigm shift. It's not just about accelerating faster or increasing range. It's about creating an energy system with behavioral intelligence that evolves alongside the driver and redefines what it means to drive an electric car. The most impressive thing is that all of this happens automatically, without any input from the driver. And this isn't just superficial behavior. The battery operates with up to 47 distinct internal modes, activated according to the detected scenario. These patterns adjust everything from recharge speed to heat dissipation, always with the goal of preserving the cell's health and ensuring the best possible performance. It's as if the battery knows, every second, the ideal strategy for dealing with everything happening around the car, and reacts with surgical precision. One of the most critical elements of any battery is the separator, the very thin membrane that prevents the positive and negative terminals from touching. When it fails, the result can be literally explosive. To avoid this risk, Tesla developed a smart polymer separator that automatically contracts when it detects any damage. This means that, even in the face of impacts or internal failures, the cell can close the door before a short circuit occurs. This structural integrity-sensitive layer works in conjunction with an advanced electrolyte, an ionized liquid that increases ion mobility by up to 400% compared to previous versions. The result? A faster and more evenly distributed charge, reducing heat spikes and accelerating battery recharge time. The combination of fluidity, protection, and adaptability creates an extremely resilient cell, far beyond what any conventional lithium-ion battery could offer. This thermal and structural intelligence completely transforms the user experience. While conventional batteries suffer from extreme temperatures and rely on external intervention, this technology acts on its own. It detects problems, corrects them, and protects itself without relying on additional software or human intervention. The material responds on its own, ensuring safety even if the car's electronic system fails. It's as if the battery has a survival instinct. The versatility of this technology opens doors to new applications. Autonomous vehicles, for example, can benefit enormously from this energy autonomy. Imagine a car that sits idle for weeks and, when turned on, the battery is practically perfect, ready to travel hundreds of kilometers. Or delivery fleets operating in extreme conditions, relying on cells that read the environment and adapt to it. This idea of a battery that transforms internally completely changes the way we view energy in everyday life. Instead of a component that wears out over time, we have a system that adapts, preserves itself, and consistently delivers maximum performance. This reduces the need for maintenance, increases user confidence, and paves the way for increasingly autonomous cars, including in terms of energy. With these advancements, Tesla appears to be abandoning the logic of the battery as a consumer item and embracing the vision of a living, responsive, and cooperative energy system. Every layer of sensors, every internal reaction, makes the Model 2 more than an affordable electric car. It becomes an extension of the surrounding environment, reacting to cold, heat, immobility, or heavy use, and doing so silently and precisely. Inside this battery, with its almost biological behavior, lies an architecture that seems straight out of a science fiction film. Instead of a single giant cell, Tesla divided each energy unit into 64 independent microcells, arranged in a fractal-inspired pattern. It's as if there were a microscopic city inside the battery, where each neighborhood has its own functions, structures, and even security systems. This arrangement allows for something unprecedented. If a microcell fails, it is automatically isolated without affecting the rest of the system. This drastically reduces the risk of cascading failures, common in traditional batteries. The loss of a cell doesn't paralyze the assembly. It only slightly reduces its capacity until repair is made. And this repair has been optimized to the extreme. Robotic arms can remove and replace a damaged microcell in less than 12 minutes, without disassembling the entire battery. At the center of each cell is a solid doped aluminum core, responsible for about 60% of the energy generated. Because it's solid, it eliminates risks such as electrolyte leakage or dendrite formation, those metallic structures that cause short circuits. Furthermore, it supports a surprisingly high ion transfer rate, comparable to the first prototypes of glass lithium-ion batteries that never reached the market. Surrounding this core, a gel ring containing lithium-rich ionic compounds completes the remaining 40% of the cell's power. This ring not only delivers energy, but also regulates everything around it: heat, voltage, and mechanical deformation. Its thermal conductivity is more than twice that of conventional electrolytes,